STM stores the multiple data items, and for every item you require one clock cycle. If you are storing 10 items, you require 10 clock cycle. Multiply instructions takes a varying number of cycles depending on the value of the second argument. This depends on the second argument. So how long it is, whether it is a byte or whether it is an half word or whether it is a full word. So this is what you know, because multiply instruction takes more than one execution cycle, and there is no fixed number of cycles for this, because it depends on the length of the second argument. Now ARM pipeline dependencies. To understand how to schedule code efficiently on ARM, we need to understand the pipeline and dependency. I want to write a program, assembly code, and schedule it efficiently for execution. So for that, I need to understand the pipeline, and the dependencies within the pipeline. If I understand the pipeline, complete pipeline, and the dependencies, then I can go for writing a code and schedule it efficiently for execution. Now, now since we are considering ARM9 TDMI processor for this, I have this ARM9 TDMI uses 5-stage pipeline processor: fetch, decode, execute, LS1 and LS2. Now what fetch basically does is, that means that any clock cycle, and you can perform these 5 operations, five operations in parallel you can perform. Now what is fetch? Fetching an instruction from the memory to the processor core using the program counter, because program counter guides the fetch operation, because that tells which is the next instruction to fetch from the memory. Decode decodes the instruction that is fetched and identifies the opcode of the instruction, and this stage also involves reading the required source operand. And execute performs the ALU operation, arithmetic and logical operation, or this basically computes the result or the answer for the data processing instruction. And for load and store, the execute computes the address. This is what you got to remember. Address is not the result or the answer. For all data processing instruction, this computes the result. For load and store instruction and load, store and branch instruction, this computes the address. Now LS1, why it's called LS1? Because load and store 1, load and store 2. Load and store 1, here load or the store instruction, using the address that is computed here, they'll go for performing either the read or the write operation to the memory. If it is a load instruction, using the address computed here, it will read from the memory. If it is a store instruction, using the address computed here, it will write to the memory. So that is what is LS1. And this LS1 stage is not necessary for the data processing instruction. They bypass this, or this stage has no effect on those instructions. And LS2 is used only by the load instruction. Now when you're loading, and that too, this LS2 will be used when the instruction is LDRB, LDRH, because and this stage LS2 will not be used by LDR. It will be used only by LDRB and LDRH. LDR, why it is used only by LDRB and LDRH? Because this stage basically does the sign extension. Here address is computed, here the data is read, and say it is LDRB. For LDRB, the address is computed here, and that byte is read from the memory in this stage, and after reading that byte data, while loading it into the register, what load ultimately does, writes to the register, loads the data to the register. Now what is read now here is a byte, but when that byte is being written to the register, it gets sign extended to 32-bit. That is what is basically happening here. Now if it is only LDR instruction, address is computed here, the entire 32-bit data is read and written to the register here itself, and this will not be used. I hope you people understood. And I think most of the things I have explained in the previous slide itself, what fetch does, what decode does. You can just go through this. Yeah, and execute, this is what it does. Execute the instruction that was decoded in the previous cycle, and the instruction that's there in the execute stage, address will be this. PC minus 8. This I've already explained you. Now because the instruction that is which is currently under execute in the execute stage. So first is fetch state, decode state, and execute stage. If I say the instruction is in the execute stage, what will be the PC value? It is PC minus 8 because the next instruction that is fetched is PC plus 8. And if similarly if I assume it is in the thumb state, it is PC minus 4. Now what this stage does, it calculates the answer for the data processing operation and calculates the address for load, store, and branch operations. And multiply takes several clock cycles, execution cycles for execution. This is what I was mentioning even earlier also, and now it is justified. Now LS1, as I already told, this stage load or store the data specified by the load or store instruction. If it is a load instruction, it reads and loads to the register LDR. It loads there itself. If it is LDRB or LDRH, it will go with the LS2 stage also. And for other instructions except load and store, this stage is bypassed. Now LS2 sign extend the data loaded by the byte or offward instruction. That is what I was mentioning. LDRB or LDRH, the sign extension takes place. This is the pictorial representation of the pipeline, 5-stage pipeline processor of ARM 9. Fetch, decode, ALU or execute, LS1, LS2. Now the instruction which is here, what is its address? PC minus 8. The instruction which is here, what is its address? PC minus 4. The instruction that is currently fetched, where do you find its address? PC. This LS1 obviously PC minus 12 and LS2 PC minus 16. Now, how does the pipeline affect the timing of the instruction? Here I have the example. Now how the pipeline is going to affect the timing, or in other words, so why it is not possible to perform the execution of the next instruction in its designated clock cycle. Now that is what we are going to learn here, and that we call it as pipeline hazard or pipeline interlock. If it's not possible for you to perform the execution of the instruction inside the pipeline in its designated clock cycle, then we say it is a pipeline hazard or a pipeline stall. In order to explain this, I am taking this example. Now this example, there is no pipeline interlock, there is no pipeline hazard. So add R0 R0 R1, add R0 R0 R2. Now what happens in the first clock cycle, we have R0 plus R1 being done and the result goes to R0. In the second clock cycle, see the second instruction is dependent on the first because the result R0 is required here. R0 is required here, and this need not wait. Even though this is dependent on this, this second instruction need not. There is no stall cycle, and it gets immediately executed. So R0 plus R2 in the second clock cycle. Why it gets immediately executed? Because there is a technique called as forwarding technique. Using that technique, so the result that is computed here, let me go back to the pipeline here. Now see, when the first instruction, first add, this add is here, the second add is here. Now when this executes, you have the result in R0. This R0 will be immediately fed back to this because in the decode stage you have the second add instruction. What is decode is? Identifying the opcode of the instruction and reading the source operands also. Now the one of the operand for the second instruction is R0, and this is available only after this finishes its execution. Now the moment this finishes its execution, this will immediately feed it back to the decode stage and it can read there, and the second addition can happen here only. So this I will show you with the diagram. Yeah, here I have written. See, I have not written properly. So this is ALU, your execute stage. This is LS1 and this is LS2. Now here I am assuming, and previous to this is the decode stage, and ALU has two inputs. You can see here. This is one input, this is another input, and this is the output. What you get? Output. The moment you get the output of the first add instruction, you see here, it is fed back to the ALU input. That means by the time the second addition instruction comes here, the result is available. The result is available. It is not only fed back. Now we don't call this as feeding back. We call it as forwarding, because we are sending the result required to the next stage ahead of one cycle. Hence it is called as forwarding technique. You should not call this as feedback. Now here Again we are forwarding it from here to the back to the ALU input. Again we are forwarding it from here to the back to the ALU input. All these things you'll understand in the advanced computer architecture when you go to the 7th semester. Right now that is not required. Now if you understood the concept, that's fine. Yeah, now I understood now why this need not wait. Even though this is dependent, data dependent on this need not wait, because the moment this finishes its execution, the result is fed back. Sorry, I should not say fed back. So the result is forwarded back to the ALU input. Back to the ALU input. Now, so example shows one cycle pipeline interlock caused by the load use. Now observe now the first instruction is this, and this is the source instruction. The instruction which produces the data is called as the source, because this is producing R1 destination register, and the same thing is being used as input to the second instruction. This is called as destination. So since R1 is used as input here, this is destination, this is source. Now here, so one cycle pipeline interlock or one pipeline stall is required, or one pipeline cycle wait is required. How? We'll see now. See here. So first clock cycle, yeah. Now let us assume the LDR instruction is already inside the execute stage. When LDR is inside the execute stage, what will be the next instruction previous to it? That is add instruction. Now LDR is executing. Now what execute for LDR is computing the address, that is R2 plus 4. Now what type of addressing mode is this? Pre-processing. This, so the pre-index without write back. Pre-index without write back. Now with write back, if you want to do, you have to put an exclamation symbol here. Now pre-indexing without write back. Now that means R2 will be added with R4. That is the address. So from that the address is computed here. Now what has happened in the next cycle? Now we have add instruction in the ALU and LDR in LS1 stage. What LDR is doing in LS1 stage, using this address which is computed, it is reading from there and writing to the destination register R1. That is happening here. Now when we have LDR performing in LS1, so this cannot execute. Why it cannot execute? Because R1 is not yet available. R1 will be available the moment this finishes this stage. Hence see, this is a dash. This is a dash. And when it goes to LS2, now this can execute. Now in clock cycle 2, addition is not executed. In clock cycle 3 it is executing. Why it is executing? In clock cycle 3, LDR has finished writing to the register R1, and that is immediately forwarded back to the ALU input, and it is available for the add instruction, and it gets executed. So this one cycle delay is there. One cycle pipelines. That means the designated clock cycle for add instruction to execute was cycle 2. It's not possible for it to get executed in cycle 2 there, because R1 is not available, and R1 is available only after the third clock cycle. So in third clock cycle it is executing. And why dash here? Because for add, it's a data processing instruction, and this is bypassed. It is not required for this. Hope you understood. Next, this is another example, shows one cycle interlock caused by delayed load use. See, load, this is the load. Observe here, LDRB it is. In the previous example we took LDR. Now for this instruction, so this is not required, this is bypassed. Now here LDRB, R1, R2, and again pre-index without write back. Now add. Observe this second instruction is not dependent on this, because R1 is not used as input here, but R1 is used as input here. This is a delayed load use. The result of load is used after some delay. Now observe now. Assuming in ALU I have LDRB instruction, in decode obviously add should be there, in UOR is fetched. What is UOR? XOR operation. Now add can happen, this can execute. Observe here. Now in the second clock cycle, so here the address is computed, LDRB is computed R1 plus R2 plus 1. Now in the first clock cycle. In the second clock cycle, now what LDRB is doing is reading from this memory location and writing it in. Will it write to the R1 here? No, it just reads from there. And second clock cycle we have this executing R0 plus R2. This is happening. And in the third clock cycle you can observe UOR is not executed. UOR is not executed. It is executing in 4th clock cycle. Add is here, and this is not doing no effect, nothing. And LDRB, it is sign extending the byte to 32 and then writes to the register R1. The moment it is written, now UOR can execute. Now this UOR, it is repeating even for the 4th cycle also here because of this one cycle interlock cast. Now if I interchange these two, now if I put add after and UOR here, how many cycle interlock will be there? The 2 cycle interlock cast, because now after add, in the place of add you just put UOR, in the place of UOR you put add, UOR comes here, UOR, and here it can execute again 2 cycle, here 1 cycle interlock. So one time it is repeating. If I assume UOR here, UOR, these two, this is a stall cycle, this is again second is a stall cycle, 3 is a stall cycle, and it can execute here. So UOR, and add comes here. Hope you understood. And this shows why a branch instruction takes 3 cycle. When I explained earlier, I told the branch instruction, it takes 3 cycles to execute. Now 1 cycle for the branch to execute and 2 cycles for flushing the pipeline. Observe here. Move R1, 1, B case 1. Now what happens in the execute cycle for this? Computation of address will happen. Now the address, where the control should jump. Now when by the time it jumps here, these two will be entering into the pipeline. This is an execute stage, this will be in the decode stage, and this will be in the fetch stage. Now when the control transfer here, now we don't want these 2 instructions to get executed. Now I have to remove these 2 instructions from the pipeline. In order to remove them, how many instructions I got to remove now? 2 instructions. So I have to apply 2 additional clock cycles to get these 2 instructions out of the pipeline. Hence, any branch instruction, it takes 3 cycles. 1 for computing the address, and 2 more cycles for removing the 2 instructions which I've already got into the pipeline. Why 2 instructions only get into the pipeline? Because if I assume the branch is in the execute stage, so how many instructions will be there previous to that? 1 in the decode and 1 in the fetch. Always 2 instructions will be there, and to take out these 2 instructions out of the pipeline, you got to apply 2 cycles. Now scheduling of load instruction, okay, will understand this example we are considering now. Now what this example will do, anything you write in uppercase, it will convert it into the lowercase, and this is a C function to typically do it. In is what? The pointer pointing to the string which you have written in uppercase, and out is a pointer which is pointing to some memory location, and where all the letters which are converted from uppercase to lowercase are written. Now I have one integer variable C. Now here C is equal to star in plus plus. This is post increment. First assign the content pointed by into C, and then I'm checking C greater than A. Now if you write anything inside the single quote, it will take the ASCII value. I don't know whether you know the ASCII value of A, uppercase A. ASCII value of uppercase A is 65. ARM, everything, it will be treated in hexadecimal value. So 65 hexadecimal value is 41. Okay, now let me forget for time being the hexadecimal values. I'll go with the ASCII values. Now say for example, I have something written in uppercase Harish. Let me write here. I'll open a notepad. Harish written in uppercase, or instead of Harish ABC, let me take it will be easy. ABC written in, this is my string to which in is pointing, in is pointing. Let me open this also, make it little small. I'll keep here. Yeah, I have written ABC here. In is pointing to this. Now what I'm doing here, C is equal to A. I'm assigning A. Now it's an unsigned int. What goes to C is ASCII value of A is 65. 65 goes to C. Now I'm checking if C 65 greater than or equal to 65. Now the A in uppercase A is written in single quote. For A, I'll write here. For uppercase A, ASCII value is 65 and hexadecimal equivalent of 65 is 41. And similarly, uppercase B, it is 66 and 42. So this is the ASCII. This column is ASCII and this is hexadecimal equivalent of them. Okay. Now I'm just taking 65 is greater than or equal to 65. Anything single quote if you write, it will take the ASCII value. So condition is true. It comes here because now I need to convert this uppercase A into what? Smaller case A. How it is happening, you can observe here. C is how much now? 65 plus let me write here. C value is 65 plus now uppercase A hexadecimal value is 97. Uppercase A ASCII value is 97 minus and A 65. This is how we are doing. This is the logic what we are using. So 95 minus 65 plus, so 7 minus 5 is 2 and 9 minus 3 is 32. Okay, if I press enter and if I add these two, I get 97. So 97 is the ASCII value of lowercase a. That is how we do it. Now C is 97. Now and the same thing I'm storing it into the one more pointer out. Now out gets say for example this is out. Now out gets lowercase a. Next, now it goes to the do while again. Now what goes to C is B and B hexadecimal ASCII value is 66. Now it is 66 here. C value is 66 plus A is 97 obviously and B is 66. So this is 31. Okay, 97 minus 65 was 32. It is 31 now. 31 and this is 66. It is 90. Oh no. This is sorry. No, this is 65 itself because lowercase a 97 minus uppercase a 65. Now this is 32 itself. And this is 98. 98 is the ASCII value of lowercase b. Now C gets 98 and what goes to out is B. And then next again what C 66 67 it is and hexadecimal equivalent of 67 is 43 and this is C. Now here this is 67. Now this is 99 and 99 goes to C and this is C. They get C. Now you have your uppercase ABC converted into lower. This is what the logic. Okay, this is what the example we are considering now. Now scheduling the load instruction, we are discussing. This is what the high-level program. To understand how to schedule the load instruction, I got to convert it into an equivalent assembly code. Now this is the equivalent assembly code for this. This is just translated into an assembly code right now. String to lower, because this what this does, it converts the given string into the lowercase. Now what I'm doing now, this is what in R1 here in was the pointer. Now I'm zooming. Now R1 is holding the address of your source string. From there I load the first character to R2, and this is post increment, and then subtract. Now this logic, c greater than or equal to a and c less than or equal to z, is implemented using this 0 less than or equal to c minus a current character minus a less than or equal to z minus a. Now what I'm doing here, now after the first character is loaded into the register R2, from the first character I'm subtracting the ASCII value of uppercase A, and then I'm comparing that with R3 16 in order to check whether it is in this range lowercase a to z, and then if it is lower than or same, I'm just adding this 20. It's nothing but R2 is equal to R2 plus this 20, that is added, and the result goes to R2, and then you store it back to the memory location, compare with 0. So this 0 is the termination character which we are taking for this string, and repeat this until all the characters in uppercase are converted to the lowercase. The logic also written here. Now copy C to this, and then from C you are subtracting the ASCII value of A, it goes to R3, and then I check whether C it is less than or equal to this, less than or equal to Z minus A I'm doing. So uppercase Z, I think it is 91 minus 65. Now you'll get it as 26. Less than C is less than or equal to that. Then if the condition is true, C is equal to C plus 97 minus 65, the one which we did in the previous example here.